right. Well, good morning, everyone. I want to thank everyone for joining us this morning. We're going to give people a couple minutes to start filing in. I see folks coming in now. So while folks are joining us this morning, I think it's a good idea just to go over some introduction, go over some house rules for the webinar today. We have a great panel for you all today. We have representatives from CEM, GFS Chemicals, Glass Expansion, and of course, Inorganic Ventures. So we have four short presentations to run through. Then we're going to do a Q&A session at the end. So if you have any questions, please use that Q&A box that you'll see. So if you have any questions, try to use the Q&A box down at the bottom instead of the chat, just to make sure we can answer them live. If you enter them into the chat, that's okay too. We'll try to catch them, but we'll be using that Q&A box for the majority of this. So really, we got this crew together this morning because we're all going to be attending Analytica early, I guess, mid next month. So a few weeks away from Analytica. I know we have a poll if you guys are planning on attending Analytica, if you wouldn't mind taking the poll that should be popping up for you guys here in a second. This is round two of what we're calling ICP Alley. We did this with this same crew earlier in the year at PitCon in Boston, and it was really successful. So we wanted to do the same thing again at Analytica. So we hope you'll join us. It'll be the first time that Analytica is in the US this year. So should be a really good show. We're all super excited for it. And I hope to see you all there. So this morning, we're going to start off with Howie from CEM, and he's going to take us through our first presentation of the day. So Howie, I'll let you take it from here.
All right, thanks, Mike, and good morning, everyone. Thank you for taking the time to join us. We're all very excited about Analytica USA and especially our ICP Alley, where the four of us will be teaming up to hopefully have some good conversations and help you guys out. So let's go ahead and get started with the sample prep. So to begin with, as far as CEM goes and the sample digestion, our goal, okay, the solution is a solution. So what do I mean by that? So what we are trying to do to solve your problems is to give you a nice homogeneous solution for your OES and mass spec analysis. These systems require a nice, steady, constant signal in order to generate the data, and the solution that we provide should help you out there. So why do we focus on pressurized? Well, the relationship between temperature and pressure, we're able to elevate the temperature of our reagents. This example here, we've got nitric acid at open vessel goes to 125 Celsius. Once you pressurize that, we routinely run at 200 degrees plus, even up to 250 C just for nitric. So what this does, it raises the oxidative potential, makes it a pretty nasty oxidizing agent, which then also helps us reduce sometimes the need for sulfuric and even hydrogen peroxide because of this increased temperature. Additionally, that's less acid that you have to purchase, is also less chance for contamination. The fewer reagents, lower your chance for contamination. So why microwaves? Well, just like we microwave anything at home, it's fast. And we'll talk a little bit why microwaves are faster than the conventional methods. So 23 plus years is one of my favorite slides. Here's our conductive versus microwave. So hot plate, for example, most of us have been there and lived that life before. Resistive wire heats up ceramic plate, heats up glass beaker, heats up liquid. A lot of transfer of energy. Fairly inefficient. It takes a lot of time, and then you have to go back. Sometimes you have to add acid so it doesn't go to dryness. Now you've got potential cross contamination from sample to sample because you're removing the reflux glass. Microwaves. Well, we use very specific materials and the dipole moment of our solution in order to absorb that energy for a fast reaction that causes that fast heat up. That's why the microwave is heating up so fastly, because of that dipole moment absorbing the microwave energy, converting it into the temperature. So here's a basic list, but I like to use this as a daily checklist when I go into the lab and I'm generating data. Because as we all know, there's a stacking effect. All of these little things, you know, you're a little dirty here, or your reagent may not be as pure, your water, all of these can add up and provide bad data, and it has nothing to do with technique, just things that we can do for good laboratory practices to generate good data. Reagent purity, kind of a no-brainer, but this is one of those things that it kind of depends on your level of analysis. So if you're doing percent level analysis versus ppb, obviously there's a big gap in there of how pure your sample needs to be. We do a lot of ppb work for our collateral, for customer samples, posters, anything like that. And we lean on our friends at GFS Chemical to provide us with the ultra pure grade, and that has worked out fantastic for us. Um, so one example that we've got here listed is if your acid has 100 ppb of nickel in it, you use 5 mils of that in your digest, then you dilute up to 100 mils. Well, you just introduced 5 mils potentially of nickel into your analysis, and it has nothing to do with the sample. So being aware of your level of analysis and the purity of your acids is a good place to start. Water, again, this is one of those things, great recommendation. We know that. But yes, having the proper water, most importantly, with your standards and diluting up the volume, rinse solutions, everything that goes through the analysis needs to use this high level of high purity water. And my reminder here is making sure that the equipment is maintained and that the filters are changed and all of that is serviced properly so that you have high confidence in your water. Anything that comes in contact with your sample, whether it's the sampling, the vessels, everything needs to be clean. Reminder, we're testing for metals. So we use a lot of Teflon coated equipment. Some of our sampling tools with the, like say spatulas, scissors and knives can be Teflon coated, ceramic. We use that stuff because, again, we don't want to introduce a metal contaminant in the early stages of our process, or any stage for that matter. For our vessels, for cleaning vessels, we have a chart that is available of how we clean it based on the level of detection, much like acid. So how low you're looking, the more intense your cleaning needs to be, all the way down to taking a clean vessel, adding acid, and running it through a microwave run for a hot acid clean as well. And make sure you use plastic containers when you're storing your vessels, or at least have a good proper coating in your metal drawers when you're storing any of this stuff to prevent possible contamination. Clean work environment, clutter, wiping down the benches, the sinks, making sure that everything is well maintained. Every day, at the end of the day, we kind of do a walkthrough and make sure everything is put away, wiped down a little bit. And then at the end of the week, we do a much more aggressive cleaning, just to make sure that we're not accidentally introducing contamination that way. Verifying that the pipes and also your faucets are free of metal, because some of these, such as lead and copper and nickel, can be readily um, you know available or can leach out. So just double checking our water from that source as well. The human factor, us. Okay. I'm not saying not to you know take a shower and such, but we need to be aware that when we're in the lab, what we put on our body can also be a possible source of contamination from perfumes and deodorants and some of the lotions with the zinc and the titanium dioxides. Obviously we're all going to have on our PPE to provide that layer, but just be aware that there are possibilities especially when you're looking at the really low level analysis. And here's some more opportunities for contamination just on our person. Clean lab coats, using sticky mats so we're not pulling in a whole bunch of debris and dust and stuff from the outside world. And then, obviously jewelry is kind of be a possibility of introducing contaminants. And then of course on the like GC side of things, if you're in that world, volatiles and semi-volatiles from cigarette smoke, etc. So when it comes to the sample prep tools as well, let's think about our balances. Making sure everything's been cleaned, uh, they're calibrated, using antistatics such as a benchtop antistatic ionizer like we do in our lab. Static guns. A lot of the balances have the pieces that reside on the balance to help with that, so that the powder stays and goes down to the bottom instead of just going out. Grinding equipment, this is a possible source of contamination if the apparatus has metal components. Making sure that you're not analyzing for those metals, so understanding what those components are made of. And then also making sure that they're clean. Again, all these little checks to make sure that we're not artificially contaminating our sample, and making sure that your pipettes are calibrated and clean, and that you have good proper technique and take good laboratory practices when you are transferring samples, especially with your standards. Acid chemistry. So we talked about everything about the purity of our acid, the water cleanliness, how we clean ourselves, how we have the lab clean, the samples, the equipment. But another key factor in proper sample prep is choosing the right acid. The right acid will put it in solution. The wrong acid, no good. So making sure that you're being aware, because metal samples, if you have too much nitric in there, you can potentially passivate and create a oxide layer that can't be digested. If you're using sulfuric, but you're analyzing for lead and barium, well, you could be creating insolubles there. If you're doing HF and you're trying to analyze for calcium and magnesium, you're going to absolutely have to do a boric acid step to complex, because calcium and magnesium can form some insoluble fluorides as well. So knowing the acid chemistry and what you're trying to accomplish is another thing that you need to be aware of when we're doing our acid digestions. Here's our crazy day periodic table. It looks fun. It looks good, but it's also very useful. It is color coded, and the metals here, we have the corresponding acid for dissolution, along with some other combinations listed down at the bottom. So hit us up on our CM website. We'll be glad to send you a copy of this. There will be a link in this presentation later. Just fill it out and we'll be glad to send you one. Very useful. We use it every single day. So microwave provides a very nice solution for your sample preparation needs. Wide range of samples, from the most basic to all the way to like very complicated matrices, with some of these new materials and plastics and oils. Nobody sends us easy samples anymore. It's all this new material. But um, make sure that you're keeping your environment, your acids, your water, everything that touches the sample, everything needs to be clean. Make a checklist and be diligent about it. Be intentional that we're going to that we are not going to do anything to introduce contamination. And as always, and I'm sure everyone will echo the same, between CEM, GFS, IV, and GE, is contact us. If you have questions, contact us. That's what we're here for, and we'll be glad to speak with you and get you through anything, help you out. Come see us at ICP Alley as well. And with that, where to go for help. For CM, we do have our website. We've got five other chemists that answer our elemental.support. Pick up the phone, 1-800 number. Sometimes a 5-minute phone call beats about 5 or 6 emails going back and forth. Very simple. We answer the phone every day. I highly recommend the periodic table on Inorganic Ventures website. It's interactive. It gives you the solubility, acid choices, OES, and mass spec information for all the elements. So, highly recommend using that one. Here's the link for our Crazy Dave periodic table. And this in the lab section on the cm.com, it is a very useful tool, and it's some of our chemists standing in front of a camera, no high production quality, 2 to 3 minutes of giving a tip in the laboratory, and maybe you can find something that would be useful for you, or maybe even use it as a training tool. So I'll go ahead and wrap up, but thank you for your time, and please come see us at Analytica USA. We're in booth 1402, and we are part of ICP Alley, and all 4 of us are going to be in the same area. So look forward to it. And Mike, I'm going to hand it off to you.
Good morning, everyone. I'm going to be the third mic that you're going to hear from today. You'll eventually hear from Mike Booth again as I pull up my presentation. It's going to tail in pretty nicely from what Howie's already spoken about. We're going to have a little bit more of a focus on cleaning your labware, specifically getting people to think about the materials of construction of your labware, plastic versus glass, and even thinking about the tools that you're using that Howie mentioned, those would apply in the same situation. Some of the things that Howie already went over, kind of what goes into your results. How are you getting that number out of your ICP-MS or ICP-OES? Ideally, it would only be metals from your sample and matrix. But as he mentioned, there's also water and acid components as you're digesting these. So making sure that you're having high enough purity for your application in target area is very important there. And then, in my opinion, one of the most important things is making sure that you're not contaminating your sample or your solutions via not having adequate or appropriate containment vessels, your flasks, beakers, pipette tips, whatever is coming in contact with those the solutions that you're making, as well as instrumentation, your sample setup, your instrumentation type, where it can remove or add interferences. And then, as Howie mentioned, some of those non-contact portions, making sure that you have good laboratory practices, things that aren't going to enter your sample through the air. So when we talk about labware materials of construction, you're basically talking about some sort of glass or some sort of plastic. Your glass, depending on what level you're looking at, is going, or what elements you care about, a lot of times is going to be a big no-no until you get into your really high purity glasses, something like quartz. Not every lab is going to have those because it is a little bit more of a niche application. Your plastics, you're talking about HDPE, LDPE, Teflon. Those are your main ones that you're going to see in most labs. They can be harder to keep relatively clean than glass because you need to keep repetitively clean them, but they can reach lower levels of background contamination that they're giving you. So it is something that is very needs to be very regimented when you're talking about your plastic labware, having good programs for cleaning and continually leaching them. Your LDPE, HDPE can be pretty durable through a short to mid-term lifespan, months and years, very durable even with some of your stronger acids. They can have some problems when you get beyond that like 2 year mark. Teflon, though, it's going to have very long life. 5 to 10 years is not unreasonable expectations from those, even with putting strong acids in them all the time. The biggest thing with those is you're probably actually going to wear out and deform them from your heating and cooling processes before you're actually worried about your plastic breaking down. Teflon can be a lot more expensive, but again, you're going to buy it once, it's going to last. You're never going to have to worry about replacing it. So when we talk about cleaning, though, glass, you're gonna get it's all surface level contamination. Whatever it's giving you is going to give it to you from day one to day 100, which is why having clean glass, if you're going to use glass, is imperative because day one it gives you, if you have a poor quality glass, day one it's going to give you a ppm of contamination. Day 1000 it's going to give you a ppm of contamination. So until you get those high purity levels, you're going to always see problems with it. But it's not impossible to find glassware that fits your needs. It can be very easy to rinse, things like that. But obviously, for your HF activities, you're not going to be able to use any of the glasswares. Um, when you do get to the high purity end, the fused silica, the quartz, you can get sub PPT levels of contamination for pretty much every metallic element. We actually use that quite a bit in our lab for select applications, making and storing standards, and testing our highest purity acids that aren't hydrofluoric acid, because we've been able to test it and get repeat tests before, after changing bottles, where we're seeing in the tens of parts per quadrillion level of difference inside and outside of that bottle. So when you get the high purity glass, it's going to be very stable and not contribute any contamination. Unfortunately, that's harder to find. As we talk about your plastics with your HDPE, LDPE, those are going to be pretty common materials that you're going to see a lot of times. The bottles of your acid, your water, whatever, are going to be coming in these. They can be pretty good at your trace level, that PPB level and slightly below. Um, you can clean them up some. They do leach metals when you put acids into them. And you can keep doing that, keep reusing them, though eventually that will wear on the integrity of the bottle, which is why 1 to 2 years lifespan is not uncommon for HDPE, LDPE, depending on the acids that you have in them. Uh, they do become very brittle, particularly with your strong acids, something like nitric acid, after about 2.5 years, and can become a safety risk. They do have some transpiration occur with your smaller molecule acids, your HCl and HF, over long periods of time, particularly in the heat. You can see that actually seep through the plastic out of the pores. So something to be careful with those. But cleaning them up, a lot of times in initial use, just some dilute nitric acid, 2 to 10%, somewhere in there. We'll clean them up in a matter of hours for you to be able to get trace or trace, that 1 ppb range or less for pretty much every element. And again, you want to have good programs, making sure that you're consistently cleaning them. Most of the time, it's just going to be that dilute acid solution to clean them out. If you have something really nasty, you might use a surfactant followed by a series of dilute acids. But that's going to hold true for most of your cleaning protocols. Um, with plastics, they are going to be porous, where they can have little pockets that can hold on to previous solutions, previous levels of contamination. So that's something that you may have to watch out for if you experience high levels of contamination in a sample. You may have to isolate that container and do multiple stages of leaching on it. As we talk about Teflon, it's something that's really common in laboratories because you can get it really clean. We get it down to the low PPT, single digit PPT levels of contamination or below. that you can get there again similarly one day to 7 days, somewhere in that leaching time gets you there for most elements. And again, similar practices for your cleaning process. 1 day to 1 to 7 days of leaching with a dilute acid gets those into your lowest levels. Typically good and viable for all your acids. They don't really become brittle. One of the few things that you'll see problematic with them is, again, HCl. When you get to those higher concentrations, can actually transpire out of them. You'll see a visual like scarring of the bottle, but that's really uncommon to excuse me, really uncommon to find above 37%. It comes with a bunch of other shipping regulations, but if that is something you're coming across, that is something to worry about. Think about storing HCl above 37% in a Teflon type labware. Um, so, kind of to wrap things up, as I'm getting a little bit closer to time, I'll just slide through my last couple slides as I kind of go over what this like porous can look like from a molecular level, the exchanges that go on in the chemical process of what's happening when we're talking about that leaching process from these plastics. When you have a clean container with some nitric acid, as we have here, it's going to dissociate. You're going to have that natural dissociation. But when you're putting that into a container that has some of that sodium atoms or something like that, that fresh plastic, what it's going to do is it's going to start pulling those onto that nitrate ion and pull them out of that plastic, put that into solution. And what you'll probably find is that you need to do multiple solution rinses of it to be able to get all of that out of there, and then finally rinse it all out. And then what you're seeing happen there is actually the mash reaction where you're having a metal and an acid turning into a salt and hydrogen. But it's usually happening at such a low level, you're not really seeing any of that effect of the hydrogen. You're just seeing the salts come out, or the metals come out of the plastic to create those salts. Um, if anybody has any questions, I know I went through these last couple of slides as I was getting close to my time. Please reach out to me or post some questions here in the chat right after. And then I'll be passing this off to Ryan, the only non-Michael on this presentation. So,
Thank you, everyone, for joining us today. My name is Ryan Brennan. I'm president of Glass Expansion. And today I'm going to be continuing to discuss how to reduce carryover and contamination with a focus on an efficient and high purity sample introduction system for your ICP MS. So a quick outline as to my presentation today. I will give a quick introduction to who Glass Expansion is for those of you who are not familiar with us. The highlight of today's presentation will be Glass Expansion's Peltier Cooled Cyclonic Spray Chamber Kit, which I'll refer to as our PCC kit. The focus today will be on a collaboration that we did with Mike Ferris from GFS Chemicals using our high purity PFA PCC kit. I'll also introduce our new high purity semi-demountable torch, and we'll discuss two inert nebulizer options. And then at the end, we'll summarize the key benefits of our high purity PFA PCC kit. So, a quick introduction. Glass Expansion has been designing and manufacturing ICP sample introduction components for over 40 years. We are globally recognized for our quality and reliability of our products. Our product line includes basically your entire sample introduction system. So from the auto sampler probe all the way to the ICP mass interface cones. And we also manufacture several different types of tools and accessories that make maintenance easy. So today, the highlight of my presentation is our PCC kit, which enables a switch from the Agilent standard Scott style spray chamber to Glass Expansion's proven Tracy cyclonic spray chamber. So in a previous webinar, which was actually a pre-webinar leading up to our introduction of ICP Alley at PittCon, my colleague Randy Mercurio highlighted the PCC kit for a high throughput environmental testing laboratory. The focus of that presentation was solely on our sort of standard quartz PCC kit, but the focus was on the drastic improvements that you get in washout when switching from the Scott style design to a cyclonic spray chamber. So since we've already done all of that work, you can access that webinar via this QR code. Grace is also going to kindly include some links that you can download our application note, as well as the recording of this webinar as well. So just a quick sort of summary of the key advantages of Glass Expansion's PCC kit. We've already proven the enhanced washout efficiency. So basically you can reduce your rinse times, you can get faster sample to sample times, you'll struggle less with reruns just due to the proven design of a cyclonic spray chamber compared to the Scott style. What's nice about the PCC kit is that you've got 3 different types of interchangeable cyclonic spray chamber designs. So we have our standard kit, which is most commonly used, would be the quartz Tracy spray chamber. If you're not concerned with boron, you can use a borosilicate glass Tracy spray chamber. And then the focus of today's presentation and the work that Mike did at GFS Chemicals is going to be using our PFA, or high purity cyclonic spray chamber. The PCC kit offers fast, simple installation. It connects directly to the existing electronics and water cooling lines of the Agilent ICP-MS, so no issues there. Each kit also comes with a convenient mounting bracket. And then what's nice about the PCC kit is that we have our patent pending jet vortex interface, which provides an aerosol filtration accessory. So it's compatible with your existing method settings for either HMI or UHMI conditions. So we basically have 3 main PCC kits. Our most standard one would be the one that Mike used, which would be KT1116. And then whether you have a Q or a P or no nomenclature at the end, that just indicates what type of spray chamber is included with that particular kit. Then we have an additional kit that's compatible specifically with the Agilent OEM switching valve. And then we also have a PCC kit for those legacy Agilent ICP-MS models. So today's focus is on our high purity PCC kit. So this particular kit would be compatible with Agilent 7850, 7900, and in the case of GFS Chemicals, we use their Agilent 8900. So what's nice about our PFA PCC kit is that it's actually compatible with either HMI or UHMI conditions due to our jet vortex interface. And today's focus is really going to be on highlighting the lower background and improved detection limits that Mike at GFS Chemicals was able to achieve compared to the standard inert kit for several elements. So here are the main key components of our high purity PFA PCC kit. So I've already mentioned the PFA Tracy. Then we have our jet vortex interface, which I'll refer to as our JVI. And then we have a PTFE transfer tube. So as you can see in this photo of GFS Chemicals Agilent 8900, we have a completely inert sample path from the nebulizer to the spray chamber to the transfer tube. And then, which I'll talk about a little bit later in today's presentation, is our high purity semi-demountable torch where we're using a sapphire injector. So what actually is the jet vortex interface? So it enables an aerosol filtration adaptation or accessory to the PCC kit. You can see that it's basically placed at the exit of the spray chamber and the very bottom or beginning of the transfer tube. So that enables you to very efficiently filter that aerosol volume and aerosol size that is exiting the spray chamber and going onto the plasma. What's important about that is that you can kind of control your transport efficiency. So if you're dealing with, you know, a higher matrix sample, you can achieve HMI and UHMI conditions with a completely inert PFA cyclonic spray chamber. That's really helpful for, you know, build up on your interface cones, but you can also sort of fine tune the plasma conditions as well. Another nice feature about our JVI is that you can use either the makeup gas or the dilution option gas to achieve those conditions. So if you only have the makeup gas option on your Agilent ICP-MS, you can actually use the JVI and turn that makeup gas into that sort of dilution option gas by just connecting that through to the JVI. So a really nice feature. The other really important component of the sample introduction system that we used at GFS Chemicals to achieve these improved detection limits and lower background is a high purity torch. So this is our new semi-demountable torch design for the Agilent ICP-MS. What's nice about this is you have the ability to choose a variety of different types of injectors. So from quartz to ceramic to sapphire, and then we also do have platinum injectors available by special request. What we did in this work was we focused on using just the sapphire injector. Benefits of a semi-demountable torch is basically that you have flexibility. So you can choose from a narrow bore to a large bore, as well as selecting different materials, whether it's for chemical resistivity, or in the case of today's presentation, getting really low background for improved detection limits. We tested two of our popular inert nebulizers at GFS Chemicals. Typically, the Opal Mist is our high purity PFA nebulizer that's best for sort of, you know, the lower detection limits. But we also have our Duramus nebulizer, which is made from PEEK and is also completely inert. What's nice about the Duramus is just due to the raw materials and the construction of it is it's actually able to give us a little bit better overall analytical performance, and it has a significantly higher resistance to total dissolved solids. So in this case at GFS Chemicals, both of these nebulizers are self-aspirating nebulizers. So in order to improve our precision and also eliminate any potential contamination from peristaltic pump tubing, we were using both of these nebulizers to naturally aspirate. What we ended up choosing was the Duramus nebulizer, just based upon the overall analytical performance, and the changes in background was negligible in this case between the Opal Mist and the Duramus. So these are the detection limits that GFS Chemicals achieved. So in the first column, we have the detection limits that they had previously been able to achieve with the standard inert kit, which is sort of a PFA Scott style spray chamber, and then the detection limits that GFS Chemicals was able to achieve with the high purity PFA PCC kit. So you can see we just took a sort of a collection of those that we found to be a significant improvement for GFS Chemicals and highlighted those here, but you can see a significant reduction in the overall detection limits for these particular elements, some of which are very important to the semiconductor industry. So a quick summary of the key benefits was, and this is kind of quoting GFS Chemicals, is it was quick and easy installation with a very short leaching time. So Mike talked a little bit about leaching your laboratory ware to get, you know, those lower detection limits or reduce those sources of contamination. What they found with our high purity PFA PCC kit and high purity semi-demountable torch was that they were able to achieve trace level backgrounds after just 1 day of leaching and ultra trace levels after 7 days of leaching. That was a significant improvement in time compared to the standard inert kit. I believe it was about like a week or so faster to achieve those levels. We noted the several key elements that the PCC kit was able to outperform, notably aluminum, boron, calcium, potassium, magnesium, and sodium. I mentioned that the PCC kit is compatible with HMI or UHMI conditions, unlike the standard inert kit. That's due to the JVI, although that was not utilized, or at least in the case of the testing done at GFS Chemicals, the option and makeup gas was set to 0. Our semi-demountable torch provides application flexibility, but also a great option for ultra trace measurements with either the sapphire or platinum injector. And then our Duramus nebulizer was a great choice for versatility, durability, and just overall better analytical performance. And I mentioned that in this particular case, we relied on self-aspiration to, one, reduce potential contamination from peristaltic pump tubing, but also to get a really nice, stable, low flow rate. So just sort of in conclusion here, if anybody out there would like a free review of their sample introduction system and learn how glass expansion might be able to help your laboratory, please reach out to us at geusa@geicp.com, and either myself or my colleagues will be able to assist you. Like all of my colleagues here as part of ICP Alley, we all have several different types of resources on our website. If you have a look, from webinars, application notes, how-to guides for maintenance, it's all there on our website. We also just launched our Plasma Pro Tips, where we're introducing the Plasma Professor. So that's an exciting new launch for us from a marketing standpoint, but also a really helpful tool for those of you that are looking to sort of enhance your ICP education. So be on a lookout for the Plasma Pro Tip short videos. And thank you all for your attention. You can reach us globally. My office is located in Massachusetts, but we also have an office in Europe. And we also have our headquarters, which is based in Port Melbourne, Australia. And thank you very much for your time. And I'll hand this over to Michael Booth.
All right, thanks, Ryan. While I share my screen for my presentation, I just want to encourage everyone, if you have any questions, please make sure to drop it in the Q&A box. We're getting some great questions already, so definitely a good start of the day. So I'm going to finish up with today's presentations of talking about troubleshooting if you are experiencing poor washout on ICP OES or mass spec. All right. So the causes for washout issues, the other presenters this morning have talked quite a bit about it. Could be anything from, the element of interest. Is it having an issue with the digestion acid that was needed to get your sample into solution? Sometimes that can happen. Is there a specific material as part of your sample introduction system that's causing washout issues? So we found personally, certain elements have a really high affinity to PVC plastic, and that's what's mostly used as the peristaltic pump tubing. So we've seen if we have issues with elements sticking around in our system, if we replace that pump tubing, sometimes that can help. Ryan talked about the spray chamber design and that being so important. What I'm going to touch on today is really diving into what are some good rinse protocols you can use if you are experiencing washout issues. So making sure you're using the right type of rinse solution, and also just checking to make sure if there's anything else going on. Do you need to extend the timeout of your rinse as well as part of your method rinse? So these are the problem elements that we usually see issues with when it comes to washout concerns. So a lot of the elements here are elements that require HF to be stable in solution, and we're going to identify those in the next slide. There are some other ones, including things like bromide and iodide, which are pretty rare to be measured on ICP, but there are some specific use cases that will measure for those. Those can be very sticky and stick around, cause washout issues as well. So why are these elements such a problem? The elements in yellow that we've highlighted here, those typically require hydrofluoric acid to be in the matrix to keep those elements stable in solution. And a lot of times your method rinse solution is not going to contain hydrofluoric acid. So that lack of HF in your rinse solution sometimes can make those things stick around a little bit longer than they could if there's HF in your rinse solution. But we'll get into some of the issues with that a little bit later. The elements in brown orange color there, those are typically sticky because of nitric acid, specifically the bromide and iodide. If you are trying to measure those, you want to keep the solution matrix basic. But we've also seen that with elements like osmium, bismuth, mercury. Nitric acid can cause those elements to stick around a little bit longer compared to something like HCl. Silver is one that's pretty simple. Silver with HCl, unless the HCl is in a high excess, can cause silver to precipitate. So if you have that, sometimes you'll experience washout issues. In worst case scenario, you'll clog up the system. If you have a sample of high in silver and then you run HCl as a method rinse in between. So that could cause some silver to stick around, or like I said, worst case, clog up the system and stop your run. And then lastly, things like selenium and thorium, those seem to have a pretty high affinity towards the PVC pump tubing that we've noticed. Certain forms of thorium require HF to redissolve in solution, which is kind of a strange thing if you're familiar with some of the issues that HF can cause in nitric acid solutions. Typically, we try to keep thorium away from that, but there are specific forms of thorium that need a little extra HF to redissolve. So those are just ones to keep an eye out for. I wanted to show an example of how to dig into some raw data and see if you are experiencing a washout issue and what you can maybe do to troubleshoot that. So this was actually we had someone reach out for tech support and send us over their data. And I think this is actually a really good example of how to review some data quickly and see if you are experiencing anything. So this person was running multiple rinses and blanks and a blank before they ran their calibration curve. And I've highlighted the rinses and blank before they ran their calibration curve and then their blank afterwards. In this specific case, this was ran on ICP mass spec, but you could do the same thing for ICP OES. I always recommend if you're running a calibration curve, run a blank immediately after your highest standard, just so you can get an idea of what the washout is looking like. So let's take a look at copper first. So really what stood out to me was, I'm not sure what the difference was between their rinse and their blank solution, but it definitely looks like their blank solution might be a higher purity acid. So that might be something if you're experiencing copper issues or you want to get really low copper detection limits. In this specific case, take a look at that because typically calibration blanks will be made from a higher purity acid than just a regular rinse solution. But if you are chasing some of these elements down at low detection limits, you may want to switch over and use high purity acid as your whole rinse solution as well. Lead is really where you see a washout issue. So lead at the beginning, the purity of the acid doesn't seem to be an issue. They're all three of those readings are coming out 650, 630, somewhere in that range. So pretty consistent. The blank immediately after the high calibration standard, though, has over 10 times the amount of counts than the blanks that ran before running your calibration curve. So what that shows is you're definitely not rinsing out all the lead from that highest calibration standard. And you can see in the very last line on here is the rinse where the counts drop back down to about 873. That's, getting closer to what they were before. But typically when folks are running, calibration curve, they're running a set of unknowns on that calibration curve. The biggest concern is what if you run an unknown, the first unknown has lead concentrations up near 500 ppb, but your second unknown that you're running could have lower concentrations of lead, closer to 10 ppb or 1 ppb. And you're going to see that carryover occur. And it's going to cause really an inaccurate result. So in this situation, this is where I would check to see, does the method rinse need to be a little bit longer? Is whatever they're using as the rinse solution, does that need to be changed out? Lead is not really a sticky element that we've noticed a ton of. Typically, it'll rinse out with nitric acid. So does it need to rinse for a little bit longer? Do you need to change the concentration of nitric acid? Do you need to look at your sample introduction system? Ryan just gave us a lot of great information on that. So all those things to look out for, but this is how you can analyze your raw results. Common rinse solutions to keep on hand. Dilute nitric and dilute HCl are very common. RBS 25, I always recommend on ICP OES to run at a 2.5% solution. It has a high sodium content, so we don't recommend it on ICP mass spec, but we would recommend running this to sort of, um, you could say, kind of get the system back into close to where it was after maintenance. So kind of recondition the system between batches. And we've noticed that we've had a lot of good luck with that. Dilute water as well, or sorry, not dilute, DI water as well. Can be very effective for things like sodium, potassium, and calcium. So don't forget about that. I mentioned before adding HF to your rinse, your method rinses. Be very cautious about that. Make sure you do have an HF resistant sample introduction system for that. Ammonium hydroxide can be very effective for things like boron, and again, I mentioned bromide, iodide, and mercury. I would use this as maybe between batches if you're having issues with those getting rinsed out, or use ammonium hydroxide as a rinse if you are running in a basic environment. And lastly, HCl and thiourea. We have a product called ICP True Rinse. We've done a webinar on this previously, and we've kind of compared and contrasted different washout times using ICP True Rinse. It's very effective. So if you're interested in that, feel free to ask us questions or see that webinar as well. Final thoughts for me, really, if you're having washout issues, take a look at that raw data first, especially if you're running a calibration curve. Really look at, run a blank after your highest standard and really look at those numbers and see if you are going to experience, if you could experience some sort of washout issue that would cause an inaccuracy in your run. So once you have that, identify those elements that are going to be the issue. Experiment with different rinse solutions. Once you do that, you can probably identify the cause, and then you can work that into your method development if you need to alter the method. Or honestly, if you're doing this as you're developing your method, that's even better. But looking at those blanks in the raw data, there's nothing that's going to compare to trying to use that to troubleshoot washout issues. Lastly, just before we get into the Q&A, I will just encourage you, if you are near the Columbus area next month or you want to make the trip out for Analytica, please stop by and see us. All four of us are going to be positioned right in the same area. We call it ICP Alley, but there'll be a coffee bar there. If you stop by and see all of us, you'll collect a little pass from all four participants, and you exchange that for an ICP toolkit, which is actually really, really nice. And again, it's a good opportunity to stop by. There is a wide range of knowledge from, CEM, GFS, Glass Expansion, and Inorganic Ventures. We had folks, at PitCon, we were walking back and forth, answering questions. So if you want to talk to us in the flesh, please come out and see us. We actually do have a limited number of complimentary vouchers. So if you're interested, please reach out and we'll get you set up and get you all ready to go. So with that, I'm going to stop sharing my screen and we'll start looking at the Q&A. So lots of good questions today. All right. So first up for CEM, how can we tell it's time to replace digestion vessels? What is their lifespan?
Okay. All right. First, I'll go ahead and take that, and I'll apologize for my audio quality earlier. I had the wrong microphone selected. So what we're looking at in the lifetime of vessels is that this is kind of like tires on a car. It is going to depend on the usage, the conditions, and the frequency at which they are being run. Because you can have a set that runs for 8 or 10 years because you're running US EPA, or if you're running 250 degrees Celsius and Teflon, it is a plastic material. It's going to wear out a lot quicker. So I would go ahead and say, let's say anywhere between 1 and 200 runs, we need to start inspecting. And this is where we start to inspect the shape. At the top, the bottom, are the vessels stretching? Any other physical marks? And also check in with us because we have care and use guides for all of our vessels to kind of show you the good, the bad, and the ugly.
Awesome. Thanks. All right. Our next one up. This is a good question. Also for CEM, are there alternatives to HF to break down silicon matrices?
Yeah. HF alternatives, yeah, that is kind of like a big deal because there is a lot of regulatory and safety precautions that have to be put in place when labs are running HF, and none of us really like to use it. Uh, there's a couple that we use. Tetrafluoroboric acid is a good one as a alternative. Now, this is going to be with smaller amounts of siliceous material. Obviously, if you're digesting a pure silica or a glass type of sample, you're going to need more punching power, if you will. Another one is ammonium fluoride mixed with hydrogen peroxide is another one that we have used as an HF alternative. But again, depending on the siliceous composition, it will be limited. It's not going to have as much punch as straight HF. And again, I'll direct you to our elemental.support@cm.com, and we can provide more information on what amounts you need to use and what care needs to be taken. Thanks.
Perfect. Thank you. This next one came in, I think, Mike, during your presentation, and they had a question about what you consider dilute acid. Would that be about 2%? Or, from your team's perspective, what do you call dilute acid?
So yeah, I think 2% nitric is what is most commonly used. Anywhere from 2% to 10% is what we would consider dilute acid. We tend to range a little bit more to that 5 to 10 range, but we also have some advantages of having a much lower cost point for that than the general public. Yeah, 2 to 5% is usually plenty for everyone else. 1% nitric probably does the trick if you have the extra time. And then depending on the elements, you might also be adding 1% HF to it, particularly for a handful of those elements that Michael mentioned in his presentation that are a little bit stickier, with boron being the most common one that we see large benefits from putting 1% HF in.
Awesome. Thank you. All right. Next question, Ryan, for you. Is the PCC kit compatible with other vendors' ICP? So I guess other vendors other than Agilent.
So no, the PCC kit itself is specifically designed. So it's a water cooled Peltier module. So it's basically the standard setup on an Agilent ICP-MS is a Scott style spray chamber, whether it be quartz or the inert kit being a PFA Scott. So the PCC kit just enables sort of swapping out that Scott style Peltier module with our cyclonic. Now, other instrument manufacturers use a cyclonic spray chamber design. So we do have spray chamber options for all other OEMs, whether it be an ICP-MS or an ICP-OES, but the PCC kit itself is based upon the design of the Agilent ICP-MS.
Perfect. Thank you. Another one, I think this will be a pretty easy one for you. What is considered low-level boron testing in regards to choice of spray chamber material?
Basically, I mean, if measuring boron is important to your laboratory, if that's something that you report, you've got to use either quartz or PFA just because of the background that you'll get from a borosilicate glass sample introduction system. So that's typically the guideline that we use. But if you want the absolute lowest level of detection for boron, I think we highlighted that pretty nicely in the work that we did with GFS Chemicals, that the more pure that or the more purity of the sample introduction system, the lower levels you'll get with pretty much all elements.
Perfect.
Yep. Definitely agree. And like I mentioned in mine, you're gonna want to use a 1% HF solution on those to make sure you get that lowest level.
Perfect. And I think that kind of leads in nicely to the next question, which I think Mike might be more towards you. Can we get more information on the leaching process that was used to reach those levels? Since you'd done the experimentation, could you give information on how you did leach those components?
Yeah, so for the spray chamber, we actually just had that sit in we have a quartz beaker or that we dunked it in a 10% nitric solution for the first day's leach, and then saw that massive drop to where we got that we're in the upper hundreds of ppts without doing anything to it to getting to those low sub 100 ppt for most elements. After that 1 day leach, we were using, like I said, a 10% nitric leach. And then after that, we then had to move to a 10%, 1% HF solution that we then soaked it in multiple days to get the boron and a couple of those other straggler elements using a PFA beaker that we had. So that's generally what I would recommend, depending on whether how low you need to go. For most people's application, that 10% nitric leach after 1 day is going to get you into the range that you're looking for.
Perfect. Thank you. All right. I'm jumping around the questions a little bit. I think the next one up. Sometimes we get samples with an unknown amount of heavy metals, especially mercury. Any tips on how to clean afterwards? So I think this might be, Howie, I think this might be for a digestion vessel. Would you want to jump in and take this one?
Sure. So, all right. So we're talking about unknown amounts of mercury.
Yeah, I think it's high concentrations. Um, yeah, they don't know how much mercury is going to be in there, but it seems to me like there might be a lot of mercury in some of their samples. So, any tips on how to clean up after the digestion vessels after that?
Yeah. Basically, what I would do is, we always recommend to completely debris the liner and hot soapy water to phosphate free, the normal stuff. But then from there, I would probably just go ahead and start with a 10% acid soak after the cleaning process, after you've washed it. Run your blank. And then if that does not do it, then another thing you can do is then put in your dilute or even concentrated acid and run a low temperature microwave digestion run to get that hot cleaning as well. And again, we do have this outlined and available for you as well. And we'll be glad to send that out to you. Or see us at ICP Alley. But that's how
Perfect.
I would jump into it.
Awesome. And if that person is talking about just how to get mercury out of their system, I would recommend, using various rinse solutions. I would throw out ICP True Rinse. There was another question a little bit later about how that's used. Typically, that's not used as a method rinse. It's used as a sort of a more of a global rinse, I guess you could call it, after your batch of samples has been run. We've experienced a lot of good results getting mercury out of systems using ICP True Rinse. So that question was about how to get it out of the instrument itself. I would recommend that approach, and then also follow Howie's advice on the digestion vessels.
Yep.
So we are right up at time for today. I think we can do one more question. What we will do is any questions that we haven't answered yet, we will provide answers in writing. So you'll see a follow-up email because there are quite a few questions left. It looks like to be about 10. So all of our presenters will take a look at all the questions, get the best person to answer them, and then get those sent out to you in writing. So we do appreciate your time this morning. The last question I'll pick out was specific to me, but I think Ryan can also jump in on this one as well. Can the use of Viton Perry pump tubing minimize carryover seen from elements that are sticking to the PVC pump tubing? So I would say to that one, maybe. We've not really experimented with Viton Perry pump tubing a ton. It's on our list to do as we have some time as we enter into the slow season. But Ryan, have you heard of anything, any users that are using Viton peri pump tubing, and have they noticed anything with washout?
Uh, no, not to my knowledge. I think that with respect to the pump tubing, the only benefit that you sometimes would get would be um, like how smooth the interior surface of that tubing is. You know, like it being less porous. But I do recall several years ago. I think it might have been around the same time that Inorganic Ventures first acquired your Agilent MS. We did a PCC collaboration with I think Thomas
Mhm.
was leading the charge with that, and he did a really cool study with a whole bunch of with the PCC kit, with the Scott style, but then also a whole bunch of different you know, kind of like rinse concoctions. But then I feel as though, I don't know if he tested Viton, but he definitely did test some different types of pump tubing formulations.
Mhm.
I think the biggest difference, right, with pump tubing is replace it regularly. You know, like that was the biggest thing that what I recall from Thomas's presentation was there was one time where he did a, you know, a hot swap of pump tubing while the instrument was still on, took off like a piece that had been used for a day and put a brand new one on without changing anything else, and the blank dropped like almost
Yeah.
instantaneously. So I think just, you know, general good practice of if you run, you know, pretty much all day, every day, it's a good idea to replace that pump tubing every day before you start back up again. That's my only advice. I mean, you saw with the work that we just did in this webinar with GFS Chemicals. Obviously, they relied on self aspiration, so you're not dealing with any peri pump tubing. You're just dealing with the PTFE or FEP tubing that's used as the uptake line from the probe directly to the neb. So I that's the best thing that I could sort of think of from pump tubing formulations.
Perfect. Yeah, I would definitely recommend the same. We personally we swap pump tubing every day. It's part of our sort of come in the morning, get the instruments up and running. We always swap out that pump tubing. And you're right, we have seen Thomas did that study where he hot swapped the tubing in the middle, and you did see that washout just drop. You know, background essentially concentration drop right out.
Yeah.
So definitely some good advice. Well, I want to thank everyone who joined us this morning. I want to thank all the presenters as well. Again, if you're going to be near Analytica next month, please stop by and see us if you're going to be attending. If you want more information, please feel free to reach out. But this ICP Alley collaboration is a really good time. And I think if you have any questions, you know, feel free to stop by, talk to us in person. We'd love to help you out. And again, thank you so much for joining us. And thanks to everyone on the presenters as well.
Thanks, Mike. Thanks,
Thank
everyone.
you.
Yep. Thanks, guys.